So here's something worth thinking about as you settle in tonight. Right now, at this very moment, there are people living in space, not visiting, not passing through, living there, eating meals, brushing their teeth, sleeping in little pods while the whole structure they call home whips around the Earth at 17,500 miles per hour. They watch 16 sunrises every single day. And the thing is, we've gotten so used to this idea that it barely makes the news anymore. Someone floats around in a tin can 300 miles above your head, and you scroll right past it. But if you stop and really sit with that for a second, it's one of the most extraordinary things our species has ever pulled off. And the story of how we got there, how we went from looking up at the stars to actually building homes among them, that story is long and strange and full of the kind of human drama that keeps you up at night, which I realize is a funny thing to say when the whole point here is to help you drift off. But that's okay. Let the story carry you. If you fall asleep somewhere in the middle of a Soviet space program rivalry or a debate about oxygen recycling systems, that's perfectly fine. The story will still be here. Let's start way before anyone actually built anything. Let's start with the dreamers. The idea of a space station, a permanent structure orbiting the Earth where people could live and work. That idea is older than you might think. It didn't start with NASA. It didn't start with the Cold War. It started, really, with a schoolteacher in rural Russia who was nearly deaf and spent most of his life in relative obscurity. His name was Konstantin Tsiolkovsky, and in the 1890s and early 1900s, he was writing papers and sketches about things that wouldn't become real for another 70 years. Tsiolkovsky imagined settlements in space. He described rotating habitats that would create artificial gravity through centrifugal force. Spin a structure fast enough, and the people inside would feel something like weight pushing them toward the outer walls. He worked out the basic mathematics of rocketry, the relationship between exhaust velocity and the mass of fuel you'd need, and he published what's now called the Tsiolkovsky rocket equation in 1903. The same year, the Wright brothers flew at Kitty Hawk. Think about that timeline. Powered flight hadn't even happened yet, and this man in Kaluga was already doing the math on how to get to orbit and what you'd build once you got there. Now, Tsiolkovsky wasn't an engineer in the traditional sense. He was a theorist, a visionary. He didn't have the resources or the institutional support to build anything. But his ideas planted seeds. He wrote about greenhouses in space, about growing food in zero gravity, about the slow expansion of humanity beyond Earth. And he wrote about all of this with a kind of poetic conviction that influenced an entire generation of rocket engineers who came after him. The Soviets would later celebrate him as the father of cosmonautics, and for good reason. His theoretical framework was remarkably sound for someone working mostly alone, mostly from first principles, in a small Russian town at the turn of the 20th century. Across Europe, other thinkers were circling similar ideas. Hermann Oberth, a Romanian-born physicist working in Germany, published a book in 1923 called The Rocket into Planetary Space. Oberth laid out detailed proposals for space stations that could serve as refueling depots, as observation platforms, even as launch points for missions deeper into space. He understood something fundamental, that getting to orbit is the hardest part. Once you're up there, moving around is comparatively cheap in terms of energy. So a station in orbit becomes a kind of base camp. You don't climb Everest by sprinting from sea level to the summit in one go. You establish camps along the way. Oberth saw orbit as that first camp. And then there's Hermann Nordung. That was actually a pen name. His real name was Herman Potočnik, a Slovenian officer in the Austro-Hungarian army. In 1929, he published a book called The Problem of Space Travel, and in it, he described a wheel-shaped space station in remarkable detail. A rotating wheel, about 100 feet in diameter, with living quarters along the rim where the rotation would simulate gravity. He included a power-generating section that would use solar energy, concentrated by mirrors. He even thought about the problem of orientation, how you'd keep the station pointed correctly relative to the sun. This was 1929. The Great Depression was just beginning. Nobody was building rockets to orbit. But Potočnik was sketching out solar-powered rotating space habitats with the kind of specificity that makes you realize these early visionaries weren't just daydreaming. They were doing real engineering analysis, just decades ahead of the technology that could make it happen. Here's the thing about all three of these figures. Tsiolkovsky, Oberth, Potočnik, they were working largely independently in different countries, in different circumstances, and they all converged on similar ideas. A station in orbit, rotation for gravity, solar energy for power, modular construction. That convergence tells you something. It tells you these ideas weren't arbitrary. They were logical responses to the actual physics of the problem. When you sit down and seriously think about how humans could live in space, you keep arriving at the same basic answers because the constraints, no gravity, no air, extreme temperatures, the need for energy, those constraints push you towards certain solutions. But dreams and equations don't build hardware. For that, you need money and political will, and usually, unfortunately, you need a war. The person who bridges the gap between the visionaries and the builders is Wernher von Braun, and he's one of the most complicated figures in the history of spaceflight. Von Braun was born in 1912 in what's now Poland, grew up in Germany, and as a teenager, he became obsessed with the idea of space travel after reading Hermann Oberth's work. He was brilliant, charismatic, ambitious, and he wanted to build rockets more than he wanted almost anything else. By his early 20s, he was working for the German army, developing liquid-fueled rockets. And during World War II, he led the development of the V-2 rocket, the world's first long-range ballistic missile, built at a facility called Peenemünde on the Baltic coast, and later assembled in underground factories using forced labor from concentration camps. Thousands of prisoners died building the rockets that von Braun designed. This is a fact that shadows everything else in his story, and it should. The engineering was groundbreaking. The human cost was horrific. Both things are true at the same time. After the war, von Braun surrendered to the Americans and was brought to the United States as part of Operation Paperclip, along with more than 100 other German rocket scientists. The Cold War was beginning, and the United States wanted those minds working for them, not for the Soviets. Von Braun ended up at Fort Bliss in Texas, then later at the Army's Redstone Arsenal in Huntsville, Alabama, and he spent the next 2 decades becoming the most famous rocket engineer in America. He was a showman as much as a scientist. In the early 1950s, he partnered with Walt Disney to produce a series of television specials about space exploration that reached millions of viewers. He wrote articles for Collier's magazine with gorgeous illustrations by Chesley Bonestell, and in those articles, he laid out a detailed vision for a space station. Von Braun's station design was directly inspired by Potočnik's earlier work, a big rotating wheel about 250 feet in diameter, orbiting at an altitude of about 1,075 miles. It would house a crew of 80 people. It would rotate to provide artificial gravity at about 1/3 of Earth's gravity, roughly what you'd feel on Mars. And von Braun described it not as some far-off fantasy, but as a practical, achievable next step in space exploration. He argued that a space station should come before a moon landing, that it was the logical staging point. You build the station first, you use it to assemble and launch missions to the moon and beyond. It was Oberth's base camp idea, fleshed out with real engineering detail and sold to the American public with Disney animation and glossy magazine spreads. And here's what's fascinating. Von Braun's vision didn't happen. Not the way he imagined it anyway. The political pressures of the Cold War pushed the United States toward the moon first, skipping the station entirely. President Kennedy's 1961 speech, committing America to landing a man on the moon before the end of the decade. That speech reordered all of NASA's priorities. The station could wait, the moon could not. And so the rotating wheel, the base camp in orbit, the logical stepping stone, it got shelved. The actual history of space stations would unfold in a completely different way than the visionaries had imagined. Messier, more improvised, driven less by elegant engineering logic and more by geopolitical competition, budget constraints, and the sheer stubborn difficulty of keeping humans alive in a place that is trying to kill them in about 15 different ways simultaneously. But before any station could be built, someone had to answer a much more basic question. Could a human being survive in space at all? Not for a few minutes during a suborbital hop, but for days, weeks, potentially months? Nobody knew. In the late 1950s, there were serious scientists who worried that prolonged weightlessness might be fatal, that the human heart, evolved over millions of years to pump blood against gravity, might simply fail without that resistance, that bones would dissolve, that the inner ear, deprived of a consistent gravitational reference, would drive astronauts insane, that cosmic radiation would cook them. These weren't fringe concerns. These were legitimate open questions, and the only way to answer them was to send people up and see what happened. The Soviets got there first. On April 12, 1961, Yuri Gagarin became the first human in space, completing a single orbit of the Earth in a Vostok capsule. His flight lasted 108 minutes. He was fine. More than fine, he was euphoric. But one orbit doesn't tell you much about long-duration survival. Over the next few years, both the Soviet and American space programs gradually extended mission durations. The Soviets flew Vostok missions lasting up to nearly 5 days. The Americans, through the Mercury and then Gemini programs, pushed further. Gemini 7, in December 1965, kept astronauts Frank Borman and Jim Lovell in a capsule roughly the size of the front seat of a Volkswagen Beetle for 14 days. 14 days in a space the size of a car seat. They came back healthy, if extremely stiff, and very ready for a shower. And that mission answered a crucial question. Yes, humans could survive in weightlessness for at least 2 weeks. Their hearts kept beating. Their minds stayed sharp. They could eat, sleep, work, and function. But surviving and thriving are different things. And a capsule is not a station. A capsule is a vehicle. You ride in it, you endure it. A station is a place where you live. The distinction matters enormously because it changes what you have to engineer. In a capsule, everything is temporary. You bring all your air, all your water, all your food, and you come home before any of it runs out. In a station, you need systems that sustain life continuously. Air recycling, water recycling, temperature control, waste management, power generation. All of it running for months or years without resupply, or at least with only occasional resupply. You need room to move, room to exercise, room to maintain your sanity. You need redundancy in every critical system, because if your oxygen generator fails 300 miles above the Earth, you can't exactly open a window. And this is where the engineering gets genuinely fascinating, because building a space station isn't really one problem. It's dozens of interlocking problems, each one hard on its own, and all of them constrained by the single most punishing limitation in spaceflight: mass. Every kilogram you send to orbit costs a staggering amount of energy and money. In the 1960s and 70s, the cost was roughly tens of thousands of dollars per kilogram. So every component, every system, every bolt and bracket and oxygen tank has to justify its weight. You can't over-engineer things the way you might on the ground, where adding an extra margin of safety just means a little more steel. In space, every extra kilogram means less of something else. The engineering becomes an exercise in ruthless optimization, in finding the lightest, most efficient, most reliable solution to every single problem, and then making all those solutions work together in a sealed metal tube, hurtling through the vacuum at impossible speed. The first nation to actually attempt this, to move beyond capsules and build something you could genuinely call a space station, was the Soviet Union. And the story of how they did it begins with a rivalry, not between nations, but between two Soviet design bureaus, two groups of engineers who despised each other, led by two men whose personal feud would shape the early history of space stations for decades to come: Sergei Korolev and Valentin Glushko, two titans of Soviet rocketry, two men who should have been natural allies, and who instead became bitter enemies in a way that only the strange, paranoid world of Soviet bureaucratic politics could produce. Korolev, you may have heard of, even if the name doesn't immediately ring a bell. He was the chief designer. That was literally his title, always spoken with capital letters, always shrouded in secrecy. The Soviet government kept his identity classified for most of his career. When Sputnik launched in 1957, when Gagarin orbited the Earth in 1961, the world celebrated Soviet achievement, but had no idea who was behind it. Korolev was a ghost, the most important engineer in the Soviet space program, and nobody outside a small circle even knew his name. He was stocky, intense, with a broad face and deep-set eyes that could go from warm to terrifying in a heartbeat. His engineers respected him enormously and also feared him. He drove people relentlessly, demanded perfection, and had a temper that could strip paint off walls. But he also had vision, a sweeping, almost romantic vision of humanity's future in space. He wanted it all: satellites, crewed flights, space stations, moon landings, Mars expeditions. He saw the whole arc. And then there was Glushko. Valentin Glushko was the Soviet Union's greatest rocket engine designer. If Korolev was the architect, Glushko was the man who built the engines that made everything fly. He was brilliant, meticulous, and every bit as ambitious as Korolev. The two had known each other since the early 1930s, back when they were young enthusiasts in the Soviet rocket societies, dreaming about space flight in a country that was still figuring out how to industrialize. They'd been colleagues, even friends, once upon a time. But here's what poisoned everything between them. During Stalin's Great Purge in the late 1930s, Korolev was arrested and sent to the Gulag. He nearly died there, spent time in the Kolyma gold mines, one of the most brutal camps in the system. His jaw was broken. He lost teeth. He contracted scurvy. He came within a hair's breadth of dying in that frozen wasteland. And Korolev believed, with some justification, though the full truth is murky, that Glushko had been among those who denounced him to the secret police. Whether Glushko actually did this deliberately, or whether he was himself coerced into making statements under interrogation, Glushko was also arrested, though he ended up in a much less brutal facility, is something historians still debate. But Korolev believed it, and he never forgave it. Imagine carrying that with you, the memory of nearly dying in a labor camp and believing the man you now have to work with helped put you there. That's the emotional substrate underneath what looks, from the outside, like a bureaucratic turf war. By the 1960s, their rivalry had hardened into something institutional. Korolev ran OKB-1, the primary Soviet Space Design Bureau. Glushko ran OKB-456, focused on engines. They disagreed about everything: rocket fuels, mission priorities, technical approaches. Korolev wanted to use liquid oxygen and kerosene for his big rockets, fuels he considered safer and more practical. Glushko pushed for hypergolic propellants, chemicals that ignite on contact with each other, which are simpler in some ways but also toxic and corrosive. The fuel debate sounds technical, and it is, but it became personal. It became the vehicle through which two proud, wounded men fought for control of the Soviet space program. And this matters for our story, because when Korolev died unexpectedly in January 1966, he was only 59, went in for what was supposed to be routine surgery, and never came out. The Soviet space program lost its unifying visionary. The man who'd been holding everything together through sheer force of will was gone, and what was left was a fractured landscape of competing bureaus, each with its own agenda, its own rockets, its own plans. Korolev's bureau, OKB-1, passed to his deputy Vasily Mishin, a talented engineer, but a man who lacked Korolev's political instincts and personal authority. And now, a third figure enters the picture: Vladimir Chelomey. Chelomey ran OKB-52, yet another design bureau, and he was a different kind of operator. Where Korolev had been a true believer in space exploration, Chelomey was more of a political animal. He'd risen partly by cultivating connections to Khrushchev. He'd even hired Khrushchev's son Sergei as an engineer, which, didn't hurt. Chelomey's bureau built cruise missiles and ICBMs, but he also had grand space ambitions. He'd been working on his own space station concept called Almaz, which means diamond in Russian. And this is where our story really picks up speed. Almaz wasn't conceived as a civilian science station. It was a military space station. The Soviet military wanted a crewed platform in orbit for reconnaissance, essentially a manned spy satellite. Now, you might wonder why you'd need humans in the loop when you could just use automated spy satellites, and that's a fair question, one that would eventually be answered in favor of the robots. But in the early to mid-1960s, the technology for real-time transmission of high-resolution images from orbit wasn't mature yet. Film return satellites worked. You'd take photos on actual film, then deorbit a capsule containing the film canisters and recover them. But the turnaround time was slow. The idea behind Almaz was that cosmonauts could observe targets in real time, choose what to photograph, develop film on board, and even use a powerful telescope to watch military activities as they happened. There was something almost quaint about it, men peering through telescopes from orbit. But in the context of Cold War paranoia, it made a certain kind of sense. Chelomey's team designed Almaz as a pressurized cylinder about 20 meters long, with a large optical system for Earth observation, a re-entry capsule to return film and data, and provisions for a crew of 2 or 3. The station would be launched on Chelomey's own Proton rocket, a powerful vehicle that's still in use today. Remarkably, Proton was a beast. It could loft about 20,000 kilograms to low Earth orbit, which gave the designers a serious mass budget to work with. But Almaz was complex, and it was taking a long time to develop. By the late 1960s, the program was behind schedule, and meanwhile, the Americans were doing something that made Soviet leadership very nervous. The United States had announced plans for Skylab. We'll get to Skylab in more detail later, but the key point here is that the Soviets learned the Americans were planning to launch a space station, and they were terrified of being beaten to yet another milestone. They'd lost the moon race. Apollo 11 landed in July 1969, and the Soviet lunar program was in shambles. The idea of also losing the space station race was politically unacceptable. Something had to be done, and it had to be done fast. So here's what happened, and this is one of those stories that could only happen in the Soviet system. Mission's Bureau, the old Korolev Bureau, now called TSKBEM, proposed a shortcut. They would take the hull of Chelomey's Almaz station, which was already being built, and essentially gut it, replacing the military reconnaissance systems with simpler scientific equipment and adapting it to work with the Soyuz spacecraft that Mission's Bureau already had. They could do this quickly because they weren't designing a new station from scratch. They were repurposing hardware that already existed. It was a brilliant hack, if you want to think of it that way, or it was theft, depending on whose perspective you take. Chelomey was furious. His station, his hardware, his design, being hijacked by a rival bureau. But the political winds had shifted. Khrushchev was long gone, removed from power in 1964, and Chelomey's political protection had evaporated with him. The decision came down from the top. Mission's Bureau would build a civilian station using Almaz-derived hardware, and they would do it as fast as humanly possible. The program was called DOS, Durable Orbital Station, and the first one would be known to the world as Salyut 1. Think about the engineering challenge for a moment. You're taking a hull designed for one purpose and retrofitting it for another on an incredibly compressed timeline. The teams worked around the clock. They had to integrate life support systems, solar panels, scientific instruments, docking mechanisms, all into a vehicle that needed to keep humans alive in the most hostile environment imaginable. And they had to do it in about 16 months. That's absurdly fast for a crude spacecraft program. The life support system alone was a marvel of engineering under constraint. Let's talk about what it actually takes to keep a human being alive in a sealed container in space, because this is one of those areas where the details are just endlessly fascinating. Start with atmosphere. You need to maintain a breathable gas mixture. The Soviets used a nitrogen-oxygen mix similar to Earth's atmosphere at roughly sea level pressure. You need to scrub carbon dioxide from the air because even at concentrations of just 2 or 3%, CO2 becomes dangerous. The Salyut stations used chemical scrubbers, canisters of lithium hydroxide that react with carbon dioxide to form lithium carbonate and water. Simple chemistry, but you need a lot of canisters, and they're consumable, meaning they get used up and have to be replaced. You also need to replenish oxygen. Early stations carried stored oxygen in tanks, and later ones would use electrolysis, splitting water into hydrogen and oxygen using electricity from the solar panels. The oxygen goes into the cabin. The hydrogen gets vented overboard. Temperature control is another beautiful puzzle. In space, you might think the problem is staying warm, since space is cold. But actually, the bigger challenge is often getting rid of heat. The station is a sealed box full of electronics and human bodies, all generating heat, and in a vacuum, there's no air to carry that heat away through convection. The only way to shed heat in space is radiation. You need radiator panels on the outside of the station that emit infrared energy. The thermal control system has to balance heat from the sun-facing side, cold from the shadow side, and internal heat from equipment and crew, keeping the interior within a comfortable range. It's a constant balancing act, and the early Soviet engineers were figuring all of this out with relatively primitive computer modeling. A lot of it was done with slide rules and hand calculations, if you can imagine that. And then there's the question of how you actually get crew to the station and back. This is where the Soyuz spacecraft comes in, and Soyuz is one of the great workhorses of space history, a vehicle so well designed that, with upgrades, it's still flying today, more than 50 years after its first crewed mission. The basic Soyuz design has 3 modules: an orbital module at the front, which is a spherical section with extra living space and equipment, a descent module in the middle, the bell-shaped capsule where the crew sits during launch and re-entry, the only part that comes back to Earth, and a service module at the rear, containing the propulsion system, solar panels, and support equipment. For station operations, Soyuz needed a docking system, a mechanism that could bring 2 spacecraft together gently, align them precisely, and create an airtight seal so cosmonauts could float from one vehicle into the other. The Soviets developed a probe and drogue docking system. One spacecraft carries a probe, essentially a rod that extends forward, and the other has a drogue, a cone-shaped receptacle. The probe slides into the drogue, latches engage, and then the mechanism retracts to pull the 2 vehicles together until their docking rings mate and form a sealed connection. It sounds straightforward, but the tolerances are tight and the consequences of failure are severe. If the docking mechanism doesn't seal properly, you can't transfer crew. If it malfunctions during undocking, you could be stuck. Every piece of this system had to work perfectly, every time, in the thermal extremes and vacuum of orbit. Salyut 1 launched on April 19, 1971, on a Proton rocket from the Baikonur Cosmodrome in Kazakhstan. It reached orbit successfully, a cylinder about 15 meters long and 4 meters in diameter at its widest, with a pair of solar panel wings giving it a dragonfly-like silhouette. It was, by any reasonable definition, the world's first space station. The first crew launched 3 days later aboard Soyuz 10, 3 cosmonauts tasked with entering the station and beginning operations. They rendezvoused, approached, and docked. Or rather, they tried to dock. The probe made contact with the drogue, the latches partially engaged, but the mechanism failed to pull the vehicles fully together. The hard dock never completed. The crew couldn't open the hatch. They spent hours trying to troubleshoot the problem, but nothing worked. Eventually, they had to undock and come home without ever setting foot inside the station they'd been sent to inhabit. And then, undocking itself became a nightmare. The partially engaged latches didn't want to release cleanly, and for a terrifying stretch of time, the crew faced the possibility that they were physically stuck to a station they couldn't enter, unable to separate their spacecraft for re-entry. They eventually freed themselves, but the mission was a failure. The second crew had a very different experience, and a far more tragic one. Soyuz 11 launched on June 6, 1971, carrying cosmonauts Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev. This time, docking worked perfectly. The crew entered Salyut 1 and spent 23 days aboard, a new record for spaceflight duration. They conducted experiments, made observations, exercised, and proved that a space station could actually function as intended. By all accounts, the mission was a success. And then, on June 29th, they climbed back into their Soyuz, sealed the hatch, undocked, and prepared for re-entry. Everything appeared normal. The service module separated on schedule. The descent module oriented itself for atmospheric entry. And then something went wrong. A pressure equalization valve, a small valve designed to open automatically during the final phase of descent to equalize the cabin pressure with the outside atmosphere. Activated far too early. It opened in the vacuum of space, while the descent module was still above the atmosphere. The cabin began to depressurize. Air rushed out through an opening roughly the diameter of a coin. Now think about what that means. You're in a sealed capsule the size of a small car. You're wearing no pressure suit, because the Soyuz 11 crew flew without spacesuits. That was a deliberate design decision, and it's worth pausing on because it tells you something about the impossible trade-offs engineers face. The Soyuz spacecraft was originally designed for 2 cosmonauts in spacesuits, but the Soviet leadership wanted 3-person crews to match or exceed American crew sizes. To fit a 3rd cosmonaut inside that tiny descent module, the engineers had to remove the spacesuits. There simply wasn't room for 3 suited crew members. So the crew flew in shirt sleeves, lightweight flight garments, nothing pressurized. The assumption was that the cabin itself would remain their pressure vessel, that the hull and its seals and valves would protect them. And for 23 days aboard Salyut 1, that assumption held. But during separation from the service module, the pyrotechnic bolts that blew the 2 sections apart sent a shock through the structure, and that shock jarred the pressure equalization valve open. In vacuum, the air inside the descent module began bleeding away. Dobrovolsky, Volkov, and Patsayev had maybe seconds, 15, perhaps 30, of useful consciousness once the pressure dropped below a critical threshold. The telemetry data later showed that one of the cosmonauts apparently tried to close the valve. He'd partially unscrewed it, but the valve was located under the seats, in an awkward position, and there simply wasn't enough time. Within about a minute, the cabin pressure had dropped to near vacuum. All 3 men died of asphyxiation and exposure to the vacuum of space, likely within 60 to 90 seconds of the valve opening. The descent module continued its automated re-entry sequence flawlessly. The parachute deployed. The capsule landed softly on the Kazakh steppe. The recovery teams opened the hatch expecting to greet 3 heroes, men who'd just set a spaceflight duration record, and instead found them motionless in their seats with dark blue patches on their faces and blood from their ears and noses. They were dead. They'd been dead since before the capsule even hit the atmosphere. It's hard to overstate the impact of that moment. 3 men killed not by some exotic space hazard, but by a valve. A valve that worked exactly as designed. It was supposed to open during descent, but opened at the wrong time because of a mechanical shock that nobody had adequately anticipated. The engineering lesson is brutal in its clarity. In space, every single seal, every valve, every pressure boundary is a matter of life and death, and the failure modes you don't imagine are the ones that kill people. The Soviet space program was devastated. There was a lengthy investigation, a redesign of the Soyuz spacecraft, and a hard rule going forward. All crews would wear pressure suits during launch and re-entry, no exceptions. That meant the Soyuz could only carry 2 cosmonauts instead of 3 until a larger version was eventually developed. The program essentially shut down crewed flights for over 2 years while the redesign was completed. And here's the thing. This tragedy happened in the shadow of what should have been a triumph. The crew of Soyuz 11 had proven the concept. 23 days of living and working aboard a space station. They'd done it. The engineering of Salyut 1 itself had largely worked. But the spacecraft that brought them home betrayed them in the final minutes. The station itself would re-enter the atmosphere and burn up in October 1971, having hosted only 1 crew, and that crew didn't survive the trip back. So now, let's cross the ocean. Because while the Soviets were grappling with this tragedy and redesigning Soyuz, the Americans were preparing their own space station. And it was a very different beast, Skylab. Even the name has a different feel to it, less military, more scientific. And the station itself was genuinely enormous compared to Salyut 1. Here's how it came about. Remember how the Apollo program had produced the Saturn V, this colossal rocket with more lifting capacity than anyone really needed for anything other than going to the moon? Well, once the later Apollo missions were canceled, Apollo 18, 19, and 20 were all scrubbed due to budget cuts. NASA had leftover Saturn V hardware, rockets already built, stages sitting in warehouses. And someone had the wonderfully practical idea, what if we take the third stage of a Saturn V, the S-4B stage, which was basically a giant cylindrical fuel tank about 6.5 meters in diameter and over 15 meters long, and instead of filling it with hydrogen fuel, we convert it into a habitable space? Just gut the tank, outfit it with floors and walls and equipment, and launch it as a space station. That's essentially what Skylab was, a converted rocket stage. And because the SIVB was so large, Skylab's interior volume was enormous, about 320 cubic meters of habitable space. Compare that to Salyut 1's roughly 90 cubic meters. Skylab was a palace by comparison. It had separate areas for sleeping, eating, working, and exercising. It had a wardroom with a window where the crew could eat meals while watching the Earth roll by below. It even had a shower, a collapsible cylinder you could pull around yourself, spray water in, and try to clean up, though by all accounts it was more trouble than it was worth in microgravity. Skylab launched unmanned on May 14, 1973, on the last Saturn V ever to fly. And almost immediately, things went wrong. During ascent, the aerodynamic forces tore away the station's micrometeoroid shield, a thin aluminum skin wrapped around the workshop's exterior. That shield also served as a thermal shield, reflecting sunlight to keep the station cool. When it ripped off, it took one of the two main solar array wings with it and jammed the other one, so it couldn't deploy. So Skylab reached orbit with half its electrical power gone and no thermal protection. The interior temperature began climbing towards 60 degrees Celsius. The station was essentially crippled before anyone set foot inside it. Now, this is one of those moments where you see the real genius of engineering, not in the original design, but in the improvised fix. NASA delayed the first crew launch by 10 days, while engineers on the ground frantically designed a solution. What they came up with was a parasol, a collapsible sunshade that the crew could push through a small scientific airlock and deploy over the damaged area of the hull like an umbrella over the station. They built it in days. The first crew, Pete Conrad, Joseph Kerwin, and Paul Weitz, launched aboard an Apollo command module on May 25th, and one of their first tasks was to deploy this improvised parasol. It worked. The temperatures dropped. The station became habitable. Then, during a daring spacewalk, Conrad and Kerwin managed to free the jammed solar array wing, restoring much of the station's electrical power. It was magnificent problem-solving under pressure, and it saved a $400 million station from becoming an orbiting oven. Skylab hosted 3 crews over 1973 and 1974. The first stayed 28 days, the second 59 days, and the third a remarkable 84 days. That third crew, Gerald Carr, Edward Gibson, and William Pogue, set a spaceflight duration record that would stand for years, and the science they did was genuinely important. The Apollo Telescope Mount, a solar observatory attached to the station, produced some of the most detailed observations of the sun ever made at that time. The crews studied the effects of long-duration spaceflight on the human body, and the results were both encouraging and sobering. Muscle atrophy and bone density loss were significant concerns, but exercise helped, and the crews generally adapted well. But here's a fascinating human story from Skylab that doesn't get told enough. The third crew, Carr, Gibson, and Pogue, essentially went on strike. Well, not exactly a strike, but something close. The ground controllers had packed their schedule so tightly, minute by minute, that the crew felt they had no autonomy, no breathing room. They were exhausted and frustrated. About halfway through the mission, they pushed back. They had a frank conversation with Mission Control about workload and scheduling, and eventually, a new arrangement was reached where the crew had more control over their own time. It was one of the first real confrontations with a question that would become central to all future long-duration spaceflight. How do you manage the psychology of people living in a confined space for months at a time? You can engineer the life support, the power systems, the thermal control. But the human mind has its own requirements, and if you ignore them, the mission suffers. That lesson from Skylab would echo through every space station program that followed. Skylab was abandoned after the third crew departed in February 1974. NASA had vague plans to revisit it, maybe boost it to a higher orbit using the space shuttle, which was then under development. But the shuttle was delayed, and Skylab's orbit was decaying faster than expected due to higher than predicted solar activity expanding the upper atmosphere. On July 11, 1979, Skylab re-entered the atmosphere and broke apart, scattering debris across the Indian Ocean and parts of Western Australia. The Shire of Esperance, a local government area in Australia, famously issued NASA a $400 littering fine. It went unpaid for decades until a radio DJ eventually raised the money and settled it. So by the mid-1970s, both superpowers had built and operated space stations. Both had learned hard lessons. The Soviets had learned about the lethal consequences of pressure system failures and the critical importance of crew safety during transit. The Americans had learned about the vulnerability of large structures during launch and the psychological needs of long-duration crews. And both programs were asking the same question: what comes next? For the Soviets, the answer was more Salyuts. After the Soyuz 11 disaster, they eventually launched Salyut 2 in April 1973. But this one was actually an Almaz military station under a civilian cover name, and it failed almost immediately due to a depressurization event, probably caused by a debris puncture or a structural failure. It never hosted a crew. Salyut 3, launched in 1974, was another military Almaz, and this one actually worked. A crew occupied it for about 2 weeks and reportedly conducted reconnaissance photography. There's even a persistent and somewhat wild claim that Salyut 3 was equipped with a modified aircraft cannon for self-defense, and that it was test-fired remotely after the crew departed. The details remain murky because much of the Almaz program was classified for decades, but the idea of a space station with a gun mounted on it tells you something about the Cold War mindset that shaped these programs. Salyut 4, launched in late 1974, was a civilian scientific station and a genuine success. 2 crews visited it, with the longest stay being 63 days. But the real leap came with Salyut 6, launched in September 1977, and this is where the Soviet space station program started to mature into something truly impressive. Because Salyut 6 introduced a feature that changed everything: a second docking port. That might sound like a small thing, but it was absolutely transformative. Think about what a single docking port means in practice. You launch your station, you send a crew up in a Soyuz capsule, they dock at the one available port, and now that port is occupied. If you want to send anything else up, supplies, fuel, a replacement crew, you've got nowhere to put it. The station is like a house with only one door. Whoever's inside has to leave before anyone else can come in. And that creates a hard limit on how long you can stay, because your Soyuz spacecraft has a finite lifespan in orbit. The electronics degrade. The propellant in the thrusters slowly becomes unreliable. The seals age. Early Soyuz vehicles were rated for about 90 days in space. So even if your station had enough food and air for a year-long mission, your ride home would expire long before that. Now add a second docking port, one on each end of the station, and suddenly the whole calculus changes. A crew can be docked at one port while a fresh spacecraft arrives at the other. You can swap out crews with an overlap period, so the outgoing team can brief the incoming team face-to-face, show them where everything is, explain the quirks of the station. This valve sticks. That sensor reads a little high. Here's how you really get the toilet to work. That kind of institutional knowledge transfer turns out to be enormously valuable. But even more important than crew rotation was resupply. Because with that second port available, the Soviets could send up unmanned cargo vehicles. And that's exactly what they did. In January 1978, just a few months after Salyut 6 launched, the Soviets debuted a spacecraft called Progress. And Progress was one of those ideas that seems obvious in hindsight, but was genuinely clever in execution. It was basically a Soyuz, same general shape, same docking mechanism, same launch vehicle, but with the crew cabin gutted and replaced with cargo space. No life support for the interior, no seats, no control panels for a human pilot. Just room for supplies. Food, water, fresh clothing, scientific equipment, replacement parts, mail from home. And here's the really elegant part. Progress also carried propellant that could be transferred through fluid lines directly into the station's own fuel tanks. So not only could you restock the pantry, you could refuel the station's engines, which meant you could reboost the orbit whenever atmospheric drag pulled it lower. This is one of those moments where a seemingly simple engineering decision, adding a second docking port, cascades into a completely different operational concept. You go from short visits to a station that's essentially a disposable capsule writ large, to something that starts to feel permanent. A place that can be continuously inhabited, continuously resupplied, continuously maintained. The station stops being a destination you visit and starts being a place where people live. And people did live there. Salyut 6 hosted a total of 16 crewed missions over nearly 5 years. The longest single stay was 185 days. That's more than 6 months, set by cosmonauts Leonid Popov and Valery Ryumin in 1980. Ryumin's story is worth pausing on for a moment, actually, because it tells you something about the kind of person who ends up on these missions. Ryumin had already completed a 175-day mission the previous year. He came back to Earth, went through the grueling readaptation to gravity. Your muscles are atrophied, your bones have lost density, your cardiovascular system has to remember how to pump blood against a full gravity field. And then, he turned around and went back up for another 6 months. Not because he had to, because the cosmonaut originally assigned to the mission had a medical issue, and Ryumin volunteered to go again. Just like that. Nearly a full year of his life spent in a metal tube the size of a bus, floating in vacuum, and he raised his hand for the second round. The medical data from these long-duration stays was invaluable. Soviet physicians were learning in real time what happens to the human body when you take away gravity for months at a time. And what happens is not great, honestly. Bones lose calcium at a rate of roughly 1 to 2% per month, concentrated in the weight-bearing bones, your spine, your hips, your legs. Muscles atrophy, especially the ones you'd normally use to stand and walk. The heart, which on Earth has to pump blood upward against gravity to reach your brain, gets lazy in microgravity because the blood distributes more evenly. Fluid shifts toward the head, which gives cosmonauts that characteristic puffy-faced look and can affect vision over time. The Soviets developed increasingly rigorous exercise regimens to combat all this. 2 hours a day on a treadmill and a bicycle ergometer became standard. And they experimented with lower body negative pressure devices, essentially pants, that create a partial vacuum around your legs to pull fluid back down and give your heart something to work against. Here's the thing that made Salyut 6 so significant in the larger arc of this story. It proved that a space station could be more than an experiment. It could be an ongoing enterprise. The Soviets developed a rhythm. Launch a long-duration crew, resupply them with progress vehicles every couple of months, send short-duration visiting crews for a week or two to deliver fresh Soyuz spacecraft, and conduct specialized experiments. Some of those visiting crews included cosmonauts from other countries as part of the Intercosmos program: Czechoslovakia, Poland, East Germany, Cuba, Mongolia, Romania, Vietnam. It was partly propaganda, sure, a way to show socialist solidarity, but it was also genuine international cooperation in space, and it predated the kind of multinational crew mixing that would later define the International Space Station. Salyut 7 followed in 1982, and it was essentially an upgraded version of Salyut 6, with better solar panels, improved life support, and more scientific equipment. It continued the pattern of long-duration missions, with the record eventually reaching 237 days, set by Leonid Kizim, Vladimir Solovyov, and Oleg Atkov in 1984. But Salyut 7 is perhaps best remembered for something that went wrong, and then spectacularly right. In February 1985, after the last crew had departed, Salyut 7 suffered a cascading electrical failure. The station lost telemetry contact with the ground. It went silent. And without active attitude control, it began to tumble. Now, you've got a roughly 20-ton space station drifting in orbit, unresponsive, slowly rotating, its solar panels no longer pointed at the sun, its batteries draining, its interior temperature plummeting. Everything inside was freezing. The water supplies were turning to ice. The station was, by any reasonable assessment, dead. The Soviets could have written it off. They had Mir already in development. But abandoning Salyut 7 would have been an embarrassment. And besides, there was real value in understanding what had gone wrong and whether a dead station could be recovered. So they sent up Vladimir Janibekov and Viktor Savinykh on what might be the most audacious repair mission in the history of spaceflight. Think about what they were attempting. Normally, when a Soyuz approaches a station, the station is cooperative. It's transmitting radar signals. It's holding a stable orientation. The docking port is pointed in a predictable direction. Salyut 7 was doing none of that. It was tumbling. It was dark. It was radio silent. Janibekov had to fly the Soyuz in manually, visually, matching the rotation of a 20-ton object and easing in to dock with it while it slowly spun. This is the kind of piloting that simulators can barely prepare you for. One wrong move, and you collide with the station, damage your own spacecraft, and now you've got 2 dead vehicles in orbit and a crew in serious trouble. But Janibekov was one of the most skilled pilots in the cosmonaut corps, and he pulled it off. They docked successfully on June 8, 1985. And then they opened the hatch into the station, and what they found was eerie. It was completely dark inside. Their breath came out in visible clouds. The temperature was below freezing. Frost covered the walls, the equipment, the windows. Every surface was cold to the touch. It was like entering an abandoned ship frozen in Arctic ice, except this ship was 300 kilometers above the Earth, moving at 8 kilometers per second. They kept their winter clothing on. They worked methodically. The first priority was power. They traced the electrical fault to the sensors that monitored the battery charge levels. The sensors had failed, which caused the charging system to stop topping off the batteries, which caused the batteries to drain completely, which caused everything else to cascade into failure. A sensor glitch. That's all it took to kill a space station. They manually connected the solar panels to the batteries, oriented the station toward the sun using the Soyuz thrusters, and waited. Slowly, painfully slowly, the batteries began to charge. As power returned, they could activate heaters. As the temperature rose, the ice on the walls began to melt, and suddenly they had a new problem. Water droplets floating everywhere in microgravity, drifting into electronics, creating short-circuit risks. They spent days mopping up water with towels, wringing them out into containers, nursing the station back to life one system at a time. It took weeks, but they did it. They brought Salyut 7 back from the dead. And the lessons from that rescue, about redundancy in sensor systems, about the vulnerability of power architectures, about what happens to a station when thermal control is lost. Those lessons fed directly into the design of what came next. Because by this point, the mid-1980s, the Soviet space program was already building something far more ambitious than any Salyut. They were building a station that wasn't just a single module with 2 docking ports. They were building a station with 6 docking ports, designed from the beginning to grow over time, to have new modules added like rooms being built onto a house. They were building Mir, and Mir was going to change everything about how humans live and work in space in ways that even its designers didn't fully anticipate. The core module of Mir launched on February 20th, 1986, aboard a Proton rocket, and right from the start it represented a philosophical shift in how you think about a space station. The Salyuts were monolithic. You launched the whole thing at once, and what you launched was what you got. If you wanted to add capability, you were mostly limited to what visiting crews could carry in their Soyuz or what a Progress freighter could deliver. But Mir's core module had a forward docking node with multiple ports arranged around it, like a hub with spokes. The plan was to launch additional specialized modules over the following years, each one docking to one of those ports, each one adding new laboratories, new solar arrays, new living space, new capability. The station would grow organically, evolving over time as new modules arrived and were integrated. This modular approach solved a fundamental problem that had constrained every previous station. With a monolithic design, you're limited by the size of your launch vehicle's payload fairing, the protective shroud at the top of the rocket. Whatever fits inside that fairing is your station, period. But with a modular design, each piece only has to fit inside the fairing individually. The total station can be far larger than any single rocket could carry. And if one module develops problems, the others can potentially keep operating. It's the same logic that makes container ships more flexible than single-hull cargo vessels, or that makes modular buildings easier to expand than monolithic ones. But here's what's really fascinating about Mir, and this is something that doesn't get talked about enough. The station became a laboratory for understanding what happens when complex systems age in the harshest environment imaginable. Because Mir was designed for a 5-year lifespan, maybe 7 if things went well. It ended up operating for 15 years, and during those 15 years, almost everything that could go wrong on a space station did go wrong on Mir, and the crews and ground controllers had to figure out how to deal with it in real time. Mir became the ultimate stress test for long-duration human spaceflight, and the things that happened aboard that station during the 1990s are some of the most harrowing and instructive stories in the entire history of space engineering. So let's talk about them. The first thing you have to understand about Mir in the 1990s is the political context, because it changes everything. The Soviet Union dissolved in December 1991. One day, the cosmonauts aboard Mir were citizens of the USSR. The next day, they were citizens of Russia, a country that was economically devastated, struggling to fund basic services, let alone a space program. Roscosmos, the Russian space agency, was suddenly operating on a fraction of its former budget, and yet Mir was still up there, still orbiting, still requiring crews, supplies, maintenance, and ground support. The station couldn't just be parked and forgotten. An uncrewed station in low Earth orbit will gradually lose altitude due to atmospheric drag. Even at 350 kilometers up, there are enough stray air molecules to slow a spacecraft down, bit by bit, orbit by orbit. Without periodic reboosts from Progress vehicles, Mir would eventually re-enter the atmosphere. So Russia had to keep flying missions, keep sending supplies, keep the station alive. But the money was drying up. This is where NASA enters the Mir story in a way that's genuinely surprising. In 1993, the United States and Russia signed an agreement for what became known as the Shuttle Mir program. American astronauts would live aboard Mir for extended stays, and the space shuttle would dock with the Russian station. The official rationale was that this would build cooperation and experience for the International Space Station, which was already being planned. And that was true. But there was also a quieter motivation. The payments NASA made to Russia for crew berths and station access provided critical funding that helped keep the Russian space program afloat during its most desperate years. American dollars literally kept Mir's lights on. Think about what that means for a second. Two nations that had spent decades in a space race, each trying to outdo the other, were now financially and operationally intertwined on the same aging space station. Cold War rivals sharing a cramped tin can in orbit, dependent on each other for survival. History is strange sometimes. So by the mid-1990s, Mir was over a decade old, well past its design life, hosting both Russian cosmonauts and American astronauts, and things started to go seriously wrong. Not because anyone was careless, but because complex systems degrade and space is unforgiving to aging hardware. Let's start with the fire, February 23, 1997. Cosmonaut Alexander Lazutkin was floating through the Kvant-1 module when a lithium perchlorate canister, a solid fuel oxygen generator, one of the backup systems for producing breathable air, malfunctioned and erupted into flames. Now, fire in a spacecraft is about the worst thing you can imagine. On Earth, hot air rises, flames go upward, and you can often move away from a fire or ventilate it. In microgravity, there's no convection. A flame doesn't rise, it forms a sphere, and the combustion products just hang there, filling the cabin with toxic smoke. And you can't open a window. You can't step outside. The entire breathable atmosphere of your station is right there, getting contaminated. The fire burned for about 14 minutes. 14 minutes doesn't sound like much, but in a sealed spacecraft, It's an eternity. The crew, Commander Vasily Tsibliev, Lazutkin, and NASA astronaut Jerry Lininger, along with visiting cosmonauts, grabbed oxygen masks, but some of the masks didn't work properly. The fire partially blocked access to one of the two Soyuz escape capsules, meaning that if the situation had gotten worse, not everyone could have evacuated. Lininger later described the smoke as so thick he couldn't see his hand in front of his face. They fought the fire with extinguishers, and eventually it burned itself out when the oxygen canister was consumed. No one was killed, but it was terrifyingly close to catastrophe. The engineering lesson here is about oxygen management and fire suppression in enclosed environments. Those lithium perchlorate canisters, the crew called them candles, work by a chemical reaction that releases oxygen. They're simple and reliable, which is why they were used as backups, but they operate at extremely high temperatures, and if the canister casing is compromised or the chemical mixture is contaminated, they can burn uncontrollably. After the Mir fire, both Russian and American programs revisited their fire suppression protocols extensively. The designs of oxygen-generating systems were modified, detection systems were improved, and the fundamental understanding that fire in microgravity behaves differently than fire on Earth, something that had been studied theoretically, was now backed by visceral, lived experience. But the fire wasn't even the worst thing that happened aboard Mir that year. Just a few months later, on June 25, 1997, came the collision. And this one is a story that still makes engineers wince. Here's the setup. Russia had been developing a new manual docking system called Toru, which would allow a cosmonaut inside the station to remotely pilot an approaching Progress cargo vehicle using a joystick and a video feed from a camera on the Progress. The automated docking system, called Kurs, worked well, but was expensive. The Ukrainian company that manufactured key components was now in a separate country and charging accordingly. If Toru could replace Kurs for routine cargo dockings, it would save money. So they decided to test it. Commander Tsibliev was at the Toru controls inside Mir, watching a small monitor showing the view from the approaching Progress M34 vehicle. The problem was that the video feed was poor quality, and more critically, it's extremely difficult to judge distance and closing speed in space. There are no familiar reference points, no atmospheric haze to give you depth cues, no ground rushing past below you at a perceivable rate. You're watching a screen showing a gray spacecraft against the black of space, and you have to figure out how fast it's coming and exactly where it's pointed. Tsibliev tried to break the Progress, but the commands weren't responsive enough, or the approach geometry was off. The exact sequence of events is still debated. The Progress vehicle struck one of Mir's solar arrays, then slammed into the Spectre module. The impact punctured Spectre's hull. Think about what that means. A hole in the wall of your spacecraft, 350 kilometers above the Earth. Air began rushing out. The crew could hear it, a hissing sound, and their ears started popping as the pressure dropped. They had minutes, maybe less, to figure out where the leak was and seal it off, or the entire station would depressurize and everyone aboard would die. What saved them was Mir's modular design. Remember those docking ports, the hub-and-spoke architecture we talked about? Because Spectre was a separate module connected to the rest of the station through a hatchway, the crew could seal that hatch and isolate the damaged module. Lazutkin scrambled to disconnect the cables running through the hatchway. Power cables from Spectre's solar arrays, data cables, everything that threaded through that opening, so the hatch could be closed. He later described frantically yanking cables while the air whistled past him. They got the hatch sealed. Spectre was lost. It remained depressurized for the rest of Mir's life, but the rest of the station survived. Here's the engineering insight that matters. Modularity saved the crew. If Mir had been a single monolithic pressure vessel, like Skylab, a hull puncture of that size could have been unsurvivable. There would have been no way to isolate the breach. But because the station was built as connected but separable modules, the crew could amputate the damaged section and keep living in the rest. This lesson was carried directly forward into the design of the International Space Station, where every module can be sealed off from its neighbors. It's the same principle as watertight compartments in a ship. You accept that one section might flood, but you design the vessel so the flooding doesn't sink the whole ship. The collision also knocked out a significant portion of Mir's electrical power because Spectre's solar arrays had been major contributors to the station's energy budget. The crew spent weeks in a diminished state, rationing power, losing some of their scientific equipment, struggling with reduced life support capacity. NASA astronaut Michael Foale, who had arrived shortly before the collision, showed remarkable composure throughout the crisis, using his physics background to help the crew calculate the station's new tumbling rate by watching stars move past a window and doing the math with a handheld calculator. And here's a detail that doesn't get mentioned enough. After the collision, after the fire, after the power loss, after the near-death experiences, the crews kept working. They kept doing science. They kept maintaining the station. They adapted. Human beings in an incredibly hostile environment, living in a damaged, aging spacecraft, continued to function and problem solve. That data, that understanding of human resilience and crew psychology under extreme stress, became one of Mir's most valuable contributions to spaceflight. Because if we're ever going to send people to Mars, a journey that takes months each way, with no possibility of quick rescue, no resupply from Earth on short notice, we need to know how people handle long-duration confinement, equipment failures, and genuine danger. Mir taught us that in ways no simulation ever could. The Shuttle Mir program ran from 1994 to 1998. 7 American astronauts lived aboard Mir for stays ranging from about 4 to 6 months. Shannon Lucid set an American endurance record of 188 days in 1996. Each of those astronauts brought back not just scientific data, but operational knowledge, how the Russians managed their station, how their life support worked, how their mission control communicated with crews, what their maintenance philosophy was, and the Russians, in turn, learned from working with NASA. This cross-pollination was invaluable because the International Space Station was coming, and it would require the two programs to work together far more intimately than ever before. Mir was finally deorbited on March 23, 2001. Russian ground controllers fired the engines of a Progress vehicle docked to the station, slowing it enough to lower its orbit into the atmosphere. The station broke apart during re-entry over the South Pacific, with fragments splashing down in an uninhabited stretch of ocean east of New Zealand. 15 years of continuous human presence, of emergencies and discoveries, of improvisation and endurance, ended in a streak of light across the sky. But by the time Mir fell, its successor was already taking shape overhead. Because the International Space Station, the ISS, had been under construction in orbit since 1998, and the story of how that station came to exist is one of the most complicated tales of international engineering cooperation ever attempted. It involves politics as much as physics, diplomacy as much as docking mechanisms, and a cast of characters spanning at least 15 countries. The very first piece of the ISS, a module called Zarya, was launched on a Russian Proton rocket on November 20th, 1998. And what's fascinating about Zarya is that it was built in Russia but paid for by NASA. About $250 million of American money funded the construction of Zarya at the Khrushchev State Research and Production Space Center in Moscow. Think about that arrangement for a second. The Cold War had ended less than a decade earlier. American astronauts and Russian cosmonauts had spent the better part of 40 years in a space race defined by secrecy and competition. And now the United States was literally writing checks to a Russian aerospace factory to build the first piece of a shared space station. The reason was partly practical. Russia had the heavy-lift Proton rocket and decades of experience building station modules, but it was also deeply political. After the Soviet Union collapsed, there was real concern in Washington that thousands of unemployed Russian rocket scientists and engineers might sell their expertise to countries trying to develop ballistic missiles. Funding Zarya, and more broadly bringing Russia into the ISS partnership, was a way to keep those engineers employed on something peaceful. So from its very first bolt, the ISS was shaped by geopolitics as much as engineering. Zarya, the name means sunrise in Russian, which feels right for a beginning, was a functional cargo block, or FGB in the Russian acronym. It was derived from the same TKS spacecraft bus that the Soviets had originally developed for the Almaz military station program way back in the 70s. So the DNA of the ISS reaches all the way back to Chelomey's spy stations. Zarya provided the initial propulsion, power, and attitude control for the station. It was about 12 meters long and 4 meters wide, roughly the size of a bus, and it launched unmanned. For 2 weeks it orbited alone, this solitary Russian-built, American-funded module circling the Earth, waiting. Then on December 4th, 1998, the Space Shuttle Endeavour launched, carrying the second piece, Unity, also called Node 1. Unity was an American-built connecting module, essentially a passageway with 6 docking ports, one on each face of a roughly cylindrical node. Astronaut Nancy Curry used the shuttle's robotic arm to grapple Zarya and berth it to Unity's forward port. 2 crew members performed spacewalks to connect electrical cables and data lines between the modules. And just like that, 2 nations' hardware was physically joined in orbit. But here's the thing. Nobody moved in yet. Zarya and Unity sat there, unmanned, for over 2 years while more components were prepared on the ground. The station was like a house with the foundation poured and the frame going up, but no one living in it. The first permanent crew, Expedition 1, didn't arrive until October 31st, 2000. Commander Bill Shepard, an American Navy SEAL turned astronaut, flew up on a Soyuz rocket with 2 Russian cosmonauts, Yuri Gidzenko and Sergei Krikalev. Krikalev, by the way, is one of the most remarkable figures in spaceflight history. He'd been aboard Mir when the Soviet Union dissolved. He launched as a Soviet citizen and came home to find he was Russian. He's the kind of person who kept showing up at every critical juncture, calm and competent. The sort of astronaut other astronauts trusted completely. Expedition 1 docked with the station and began what has now been more than 2 continuous decades of human habitation in orbit. As of this recording, there has been at least 1 person living aboard the ISS every single day since November 2nd, 2000. Let that sink in. For over 24 years, without a single gap, someone has been up there, looking down at the Earth, running experiments, fixing toilets, sleeping in a bag velcroed to the wall. Now, the assembly of the ISS was an astonishing logistical puzzle. The station was built piece by piece over more than a decade, with components launched on both the space shuttle and Russian rockets. More than 40 assembly flights were required. Each new module or truss segment had to be maneuvered into position, berthed or docked, then connected, structurally, electrically, for data, for fluid lines. The whole thing had to work as a system even while it was incomplete, which meant every intermediate configuration had to be stable, had to have adequate power, had to maintain attitude control. It's like renovating a house while the family is living in it, except the house is moving at 17,500 miles per hour, and any mistake could kill everyone inside. The backbone of the station is a long horizontal structure called the integrated truss structure. Picture a steel beam stretching about 109 meters from tip to tip, longer than a football field. Along this truss are mounted the massive solar array wings that provide electrical power, the radiator panels that reject waste heat into space, and the mechanical systems that rotate those arrays to track the sun. The pressurized modules where the crew actually lives and works are clustered in the middle, attached to the truss through the node modules. On the Russian side, you have Zarya, the Zvezda service module, which provides the primary living quarters and life support on the Russian segment, and several smaller modules added over the years. On the American and international side, you have the Unity and Harmony nodes, the Destiny Laboratory, the European Columbus Laboratory, the Japanese Kibo Laboratory Complex, and the Tranquility node with its famous cupola. That gorgeous, 7-windowed observation dome that produces those breathtaking photographs of Earth you've probably seen. And here's where the international engineering cooperation gets really interesting and really complicated. The ISS partnership includes the United States, Russia, Japan, Canada, and 11 member states of the European Space Agency. Each partner built specific components and has specific rights and responsibilities. Canada, for instance, built the mobile servicing system. That's Canadarm2, the 17-meter robotic arm that crawls along the outside of the station, moving equipment and even astronauts during spacewalks. Japan built the Kibo module, which is actually the largest single pressurized module on the station, along with an exposed external platform for experiments that need direct exposure to the space environment. The European Space Agency built Columbus, a cylindrical laboratory packed with experiment racks. But here's the challenge. All of these components were built in different countries by different contractors using different engineering standards, different unit systems, different manufacturing traditions. The American segments use English units in some systems and metric in others. The Russian segments are entirely metric and follow Russian engineering standards that evolved independently from Western ones. The docking mechanisms are different. The Russian segment uses probe and drogue systems, while the American side eventually adopted the common berthing mechanism and later the international docking adapter. Even the electrical systems differ. The American segment runs on 124 volts DC, while the Russian segment uses 28 volts DC. Converters are needed wherever the two systems interface. Think about what that means in practice. Every single connection point between the American and Russian segments required careful interface engineering. Teams from both countries sitting down together, sometimes through translators, working through technical drawings that use different conventions, different symbology, different assumptions about how things should be done. And it wasn't just hardware. The software systems had to communicate. The mission control centers, one in Houston, one in Korolev outside Moscow, had to coordinate in real time, around the clock, across time zones and language barriers. There's a reason Bill Shepard insisted that the station have a single call sign. He chose Alpha, so that everyone, regardless of nationality, was talking about the same thing in the same way. The life support on the ISS is the most sophisticated closed-loop environmental system ever built for space. And it had to be, because resupply is expensive. Every kilogram of water or oxygen you launch from Earth costs thousands of dollars. So the station recycles almost everything. The water recovery system, located in the Destiny module, takes humidity condensate from the air, wastewater from the crew, and, yes, processed urine, and purifies it back into drinkable water. The system uses a combination of filtration, catalytic oxidation, and iodine treatment. Astronauts sometimes joke about it. Yesterday's coffee is tomorrow's coffee, but the water that comes out actually meets higher purity standards than most municipal tap water on Earth. The oxygen generation system electrolyzes that recovered water, splitting it into hydrogen and oxygen. The oxygen goes into the cabin atmosphere. The hydrogen was originally just vented overboard, which is wasteful. But a later upgrade called the Sabatier reactor combines that hydrogen with carbon dioxide exhaled by the crew to produce water and methane. The water gets recycled back into the system, and the methane is vented. So the station is slowly closing the loop. Not perfectly, not yet, but each improvement reduces the amount of consumables that need to be launched from the ground. And the power system is a marvel in its own right. Those solar arrays, 8 of them in the American segment alone, span an area of about 2,700 square meters combined, and they generate somewhere between 84 and 120 kilowatts of electricity depending on their orientation to the sun. But the station passes through Earth's shadow for roughly 35 minutes out of every 92-minute orbit. During those shadow periods, the station runs on nickel-hydrogen batteries, or rather, it did originally. Those batteries were replaced starting in 2017 with more efficient lithium-ion batteries, a major upgrade performed over a series of spacewalks. Astronauts literally went outside in their spacesuits and swapped out refrigerator-sized battery units on the truss structure, hundreds of kilometers above the Earth, working with their gloved hands in the vacuum of space. Each battery swap was carefully choreographed, because the power system is the station's lifeblood. Lose power and you lose thermal control, life support, communications, everything. The thermal control system deserves a moment, too, because managing heat in space is counterintuitive. In space, there's no air to carry heat away through convection. The only way to reject heat is through radiation, emitting infrared energy from large surface areas. The station generates a lot of waste heat from all its electronics and systems, and it has to get rid of it, or the interior temperature would climb dangerously. So ammonia coolant loops circulate through the pressurized modules, absorbing heat, then carry it out to the external radiator panels on the truss, where it's radiated into the cold of space. Those radiator panels are the white, flat structures you can see in photographs of the station, and they're enormous. They have to be, because radiative cooling is inherently less efficient than convective cooling. An ammonia leak, by the way, is one of the most serious emergencies the crew can face. Ammonia is toxic, and if it breached into the cabin atmosphere, the crew would have to seal off the affected module and potentially evacuate to the Russian segment, or even abandon the station. There have been a couple of ammonia scares over the years, and each one was taken extremely seriously. Now, speaking of emergencies, the ISS has had its share. Not on the scale of the mere fire or collision, thankfully, but enough to keep everyone honest. In 2018, a small hole was discovered in the orbital module of a Soyuz spacecraft docked to the station, causing a slow air leak. The crew patched it with epoxy as a temporary fix. The cause was eventually traced to what appeared to be a drill hole, possibly made during manufacturing or testing on the ground, then sealed with a plug that later worked loose. The incident sparked a tense investigation and some friction between NASA and Roscosmos over accountability. There have also been multiple instances of cooling loop malfunctions, computer failures, and close calls with orbital debris. In November 2021, Russia conducted an anti-satellite weapons test that destroyed one of its own defunct satellites, creating a cloud of debris that forced the ISS crew to shelter in their docked spacecraft as fragments passed nearby. The irony of a station partner endangering the station with its own weapons test was not lost on anyone. But perhaps the most persistent challenge the ISS faces isn't any single emergency. It's aging. The station was originally designed for a 15-year operational life. Zarya and Zvezda have now been in orbit for over 26 years, exposed to the relentless cycle of thermal expansion and contraction, micrometeorite impacts, atomic oxygen erosion, and radiation bombardment. Small cracks have been found in the Zvezda module's transfer compartment, and air leak rates from the Russian segment have been a growing concern. Engineers on the ground monitor these issues constantly, patching what they can. But there's a fundamental reality. Hardware in low Earth orbit degrades, and at some point, the cost and risk of maintaining aging systems outweighs the benefit. NASA has currently extended ISS operations to 2030, with plans to deorbit the station using a specially built vehicle. Russia's commitment has been more ambiguous, with statements about potentially departing the partnership earlier to focus on their own planned orbital station. And that brings up something fascinating about what comes next. Because the ISS isn't just the end of one story, it's the beginning of several others. Even as engineers work to keep the aging station functional, a new generation of commercial space stations is being developed. NASA has awarded contracts to multiple companies to build private successors to the ISS, stations that would be owned and operated by commercial entities rather than governments. Axiom Space has already attached a module to the ISS as a stepping stone toward building their own free-flying station. Blue Origin is developing Orbital Reef. VAST is working on Haven 1. The idea is that NASA would become a customer rather than an owner, renting laboratory space and crew time rather than bearing the full cost of maintaining an entire station. It's a fundamentally different model from anything that's come before, and whether it works depends on whether there's enough commercial demand for orbital research and manufacturing to sustain these stations financially. But there's another thread worth following here, one that takes us beyond low Earth orbit entirely. Because while the ISS taught us how to build and maintain a large structure in space, how to keep humans alive and productive for months at a time, how to manage international partnerships across language and culture barriers, all of that knowledge points toward something much more ambitious. And that something is the idea of building habitats far from Earth. Places where humans can live not just in low orbit, a few hundred kilometers up, but out at the moon or in the void between here and Mars, or eventually on the Martian surface itself. And that leap from low Earth orbit to deep space is bigger than it might sound at first. It's not just a matter of flying farther. Almost everything changes. Think about what the ISS relies on. If something breaks, really breaks in a way the crew can't fix, you can have a replacement part on a Progress or Dragon capsule within weeks, sometimes days in an emergency. If a crew member gets seriously ill or injured, they can be back on Earth inside hours. The station orbits close enough that communication is nearly instantaneous, just a slight delay through relay satellites. Resupply, rescue, real-time support from mission control. All of that is possible because the ISS is, cosmically speaking, right next door. A station at the moon, or a habitat heading to Mars, doesn't get any of that. You're on your own in ways that fundamentally change the engineering, the medicine, the psychology, everything. So let's talk about what's actually being planned, because it's real, it's happening now, and it builds directly on every lesson we've traced through this whole story, from Salyut to Skylab to Mir to the ISS. The most concrete near-term project is Gateway. That's the name NASA and its international partners have given to a small space station that will orbit the moon. Not in low lunar orbit, the way Apollo circled close to the surface, but in what's called a near rectilinear halo orbit, or NRHO. This is a highly elliptical path that takes the station as close as about 1,000 kilometers from the lunar surface at its nearest point, and swings out to roughly 70,000 kilometers at its farthest. The orbit was chosen very carefully, and the reasons are worth understanding because they reveal how much orbital mechanics shapes station design. NRHO is gravitationally stable in a useful way. It requires very little fuel to maintain, which matters enormously when every kilogram of propellant has to be launched from Earth or produced somewhere else. It also keeps the station in continuous communication with Earth, avoiding the blackout periods you'd get in a low lunar orbit when the moon blocks the signal. And it provides access to a wide range of landing sites on the lunar surface, which is important because Gateway is meant to serve as a waypoint, a place where crews arriving from Earth can transfer to a lunar lander, descend to the surface, come back up, and then head home. It's a hub, a very small hub, at least initially, but a hub nonetheless. The first two modules of Gateway are the power and propulsion element, built by Maxar Technologies, and Halo, the habitation and logistics outpost, built by Northrop Grumman. Here's what's interesting about the power and propulsion element. It uses solar electric propulsion, specifically a system of advanced Hall-effect thrusters. These are ion drives, essentially. They work by ionizing xenon gas and accelerating it with electric fields to produce thrust. The thrust is tiny compared to a chemical rocket. We're talking about the force you'd feel holding a few sheets of paper in your palm, but it's continuous. The thrusters can fire for months, slowly adjusting and maintaining the orbit with extraordinary fuel efficiency. It's the same basic technology that's been proven on NASA's Dawn mission to the asteroid belt and on many commercial communications satellites, but scaled up and applied to a crewed facility for the first time. Halo, the habitation module, is compact. We're not talking about ISS-scale living space here. Gateway, at least in its initial configuration, is going to feel more like a camper van than an apartment. The pressurized volume is roughly the size of a studio apartment, maybe 60 cubic meters or so for the core habitat. Crews won't live there permanently the way they do on the ISS. The plan is for astronauts to visit for stays of maybe 30 to 90 days, using Gateway as a staging point for lunar surface missions under the Artemis program. Between crew visits, the station operates autonomously, maintained by its own systems and monitored from Earth. And this is where it gets interesting from a life support perspective, because everything we learned on the ISS about closing the loop, recycling water, generating oxygen, scrubbing carbon dioxide, becomes even more critical when you're 4 days from Earth instead of 4 hours. On the ISS, if the water recycling system fails, you've got reserves and you can get a resupply relatively quickly. At the moon, your margins are thinner. The environmental control and life support system for Gateway has to be more reliable, more autonomous, and smarter about diagnosing its own problems. NASA has been developing what they call autonomous systems management, essentially giving the station's computers the ability to detect failures, reroute systems, and in some cases, fix problems without waiting for instructions from Houston. Because at lunar distance, communication delay is only about 1 1/3 seconds each way, which is manageable, but the real issue is that Gateway will spend long stretches uncrewed. The life support systems need to maintain the atmosphere, manage thermal loads, and keep everything from freezing or overheating even when nobody's aboard. Now, you might be thinking, okay, Gateway is a small station near the moon. That's a step forward. But how does this connect to Mars? And that's the really big question, the one that every space agency and a growing number of private companies are circling around. Because a trip to Mars isn't a few days. Depending on the orbital alignment, a one-way transit takes roughly 6 to 9 months. A full mission, getting there, spending time on the surface or in orbit, and coming home, would take somewhere around 2 to 3 years. 2 to 3 years. Think about what that means for a crew of 4 to 6 people sealed inside a habitat not much bigger than a couple of school buses. Every problem we've talked about throughout this whole story converges on the Mars Transit Challenge. Bone loss and muscle atrophy, the issues that plagued early Salyut crews and that the Soviets spent decades developing exercise countermeasures for. Those become even more severe on a Mars mission, because you can't evacuate someone whose skeleton has weakened dangerously. The psychological pressures that surfaced during Skylab that were studied extensively on Mir and the ISS, isolation, monotony, interpersonal friction, the growing distance from home, all of those intensify when the crew watches Earth shrink to a bright dot indistinguishable from the stars. The communication delay to Mars ranges from about 4 minutes at closest approach to over 24 minutes when Earth and Mars are on opposite sides of the Sun. That means no real-time conversations with mission control. No calling home and hearing your kid's voice in the moment. You send a message and wait anywhere from 8 to 48 minutes for a response. The crew has to be genuinely autonomous in a way no space crew has ever been. And then there's radiation. In low Earth orbit, the ISS sits inside the magnetosphere, Earth's magnetic field, which deflects most of the really dangerous charged particles from the Sun and from galactic cosmic rays. The ISS crew still gets elevated radiation exposure, roughly the equivalent of getting a CT scan every week or so. But it's manageable for 6-month stays. Outside the magnetosphere, on the way to Mars, you lose that protection entirely. Galactic cosmic rays, these incredibly high-energy particles that come from exploding stars across the galaxy, can penetrate spacecraft walls and human tissue, damaging DNA in ways that increase cancer risk and may even affect cognitive function. There's growing research suggesting that prolonged exposure to cosmic radiation could impair memory and decision-making, exactly the faculties you need most on a mission where the crew is making life-or-death calls without real-time ground support. Shielding against galactic, cosmic rays is brutally difficult. These particles are so energetic that conventional metal shielding actually makes things worse in some cases. The cosmic ray hits the metal and produces a shower of secondary particles, like a billiard ball smashing into a rack. The most effective shielding materials are hydrogen-rich. Water, polyethylene, even the crew's food and waste can provide some protection. Some designs propose lining the walls of the transit habitat with water tanks, which serve double duty as radiation shielding and consumable storage. Others are investigating pharmaceutical countermeasures, drugs that might help cells repair radiation damage more effectively. And there are active shielding concepts, essentially creating an artificial magnetic field around the spacecraft, but these remain largely theoretical and would require enormous amounts of power. So you start to see how every thread we've followed, the life support engineering, the structural design, the human factors research, the orbital mechanics, the hard-won operational knowledge from decades of space station programs. All of it feeds into this Mars challenge. The ISS isn't just a laboratory in the sky. It's a test bed for learning how to keep people alive and sane and functional very far from home for very long periods of time. And some of that testing is already happening. NASA and its partners have been running analog missions, simulated Mars habitats on Earth, where volunteer crews live in isolation for months at a time. Russia did this with the Mars 500 experiment, which locked 6 men in a simulated spacecraft in Moscow for 520 days between 2010 and 2011. NASA has its own program called CHAPEA, Crew Health and Performance Exploration Analog, running year-long missions inside a simulated Mars habitat at Johnson Space Center. These studies can't replicate the radiation or the microgravity, but they can study the psychology, the group dynamics, the menu fatigue, the boredom, the subtle erosion of motivation that sets in around month 4 or 5. And here's something that connects all the way back to those early Salyut crews, to Ryuman's grueling stays and the Skylab scheduling revolt. The lesson that keeps reasserting itself across 60 years of space station history is that the human element is not secondary to the engineering. It is the engineering. You can build the most elegant life support system, the most robust radiation shield, the most efficient propulsion system, and the mission will still fail if the crew falls apart psychologically. Every station program has learned this, usually the hard way, and every future program will have to internalize it even more deeply, because the farther you go from Earth, the less you can intervene when things go wrong between people. There's a concept in mission design called Earth-independent operations, and it's become a kind of organizing principle for deep space planning. The idea is straightforward. Design the mission so that the crew can handle any plausible scenario without help from Earth. That means onboard medical capability, not just first aid, but potentially surgery, dental care, psychiatric support. It means repair capability for every critical system, with spare parts and the tools and training to use them. It means decision-making authority, resting with the crew commander rather than with mission control. A philosophical shift that would have been unthinkable in the early days of spaceflight when every action was scripted from the ground. And it means something else, something that brings us right back to the question of how you build a habitat that can sustain human life for years. Because for a Mars mission, closing the life support loop isn't just desirable, it's essentially mandatory. You cannot carry enough water and oxygen for a 3-year mission. The numbers simply don't work. On the ISS, the water recovery system reclaims about 90% of the water from humidity, urine, and other sources. For Mars, you'd want that number closer to 98%, and you'd want to integrate plant growth, actual crops growing in the habitat, both for food supplementation and for their role in the carbon dioxide and oxygen cycle. There's been research on the ISS growing lettuce, radishes, chili peppers, testing which crops can thrive in microgravity with limited space and artificial light. It's early work, but it points towards something that Tsiolkovsky imagined over a century ago. A self-sustaining ecosystem in a metal shell, a tiny biosphere carrying life through the void. And this is where the story of space stations starts to merge with something even larger, something that takes us from engineering into questions about what kind of species we want to become. Because that's really what we've been talking about this whole time, isn't it? Not just metal and wiring and oxygen scrubbers, but a question. Maybe the question, about whether human beings can learn to live away from the planet that made them. Think about that arc for a moment. We started with Tsiolkovsky in his log cabin in Kaluga, a nearly deaf school teacher sketching greenhouse-filled cylinders in his notebooks in the 1890s, imagining plants growing in sunlight channeled through glass walls in space. And here we are, more than a century later, astronauts on the International Space Station, actually eating lettuce they grew in orbit, actually tending chili peppers under LED lights, actually measuring how roots behave without gravity to guide them. The line between that cabin and that orbiting laboratory is long and winding and full of heartbreak and triumph, but it's a single, unbroken thread. One species feeling its way outward, one habitat at a time. And what's striking, when you look at the whole sweep of it, is how much of the story has been about learning to fail gracefully. That's really the hidden curriculum of space station history. Every generation of station taught us something we didn't know we needed to learn, and the tuition was usually paid in crisis. Salyut 1 taught us that a cabin depressurization could kill a crew in seconds, and the cost was Dobrovolsky, Volkov, and Patsayev, 3 men who did everything right and died anyway because of a valve the size of a coin. That lesson gave us pressure suits during re-entry, a protocol that's still followed today. Skylab taught us that astronauts are not robots, that you can't schedule every minute of a person's day for months on end without something breaking. Not a machine, but a human spirit. The scheduling revolt of 1973 changed how every long-duration mission since has been planned. Salyut 7 taught us that a station can die and be brought back to life if you send the right people and give them the freedom to improvise. Mir taught us that fire and collision are survivable if you've trained for them, and that a station can outlive its designer's expectations by years if you're stubborn enough to keep fixing it. The ISS taught us that 15 nations can build something together in orbit that none of them could have built alone, and that the hardest engineering problems are sometimes not technical at all, but political, cultural, linguistic. Each lesson was expensive. Some were paid in lives. But each one added to this body of knowledge, this institutional memory, about how to keep people alive in a place that is fundamentally hostile to life. And that body of knowledge is what makes everything that comes next possible. Gateway, the commercial stations, whatever we eventually send toward Mars, none of it starts from zero. It all stands on the shoulders of every crew that ever floated through a hatch into a tin can and figured out how to make it home. Here's the thing that I find quietly remarkable about where we are right now, in this particular moment in the history of human spaceflight. We're in a transition. The ISS, this extraordinary machine that's been continuously inhabited since November of 2000, is approaching the end of its operational life. The current plan, as we talked about, is to deorbit it around 2030, send it into the Pacific. And for the first time, the next chapter isn't being written primarily by governments. It's being written by companies, Axiom, Vast, Blue Origin's Orbital Reef Consortium, others. The economics of getting to orbit have changed so dramatically, largely because of reusable launch vehicles, that building and operating a space station is no longer something only a superpower can afford. A Falcon 9 launch costs a fraction of what a space shuttle launch cost. Starship, if it fulfills even part of its promise, could reduce that cost by another order of magnitude. And when you reduce the cost of getting mass to orbit, you change everything about what's possible up there. So imagine for a moment what the next decade might look like. You might have Axiom's station, built partly from modules that were first attached to the ISS and then detached to fly independently, serving as a commercial hub, a place where companies can manufacture things that can only be made in microgravity, where researchers can run experiments, where private astronauts can visit. You might have Vast's Haven 1, a smaller station designed for shorter missions, proving out the business model. You might have Orbital Reef, a larger complex with multiple modules from different partners, designed almost like a business park in space. And alongside all of these, you might have Gateway, orbiting the moon, serving as a staging point for lunar surface missions under the Artemis program. That's a future with multiple space stations, operated by multiple entities, for multiple purposes. It's a far cry from the single fragile outpost model that's defined the last 60 years, and it's closer to what the early visionaries actually imagined. Not one station, but a network. Not a single point of presence in space, but a sustained, distributed human footprint. Now, you might be thinking, okay, but will people actually want to live and work in space long term? Is there a real reason to be up there beyond exploration and national prestige? And this is where the story gets interesting, because there are things you can do in microgravity that you genuinely cannot do on Earth, and some of them turn out to be valuable. Take fiber optics, for example. There's a type of optical fiber made from a material called ZB-LAN. It's a fluoride glass that, when manufactured in microgravity, has far fewer of the tiny crystalline defects that form when you make it on Earth. Gravity causes convection currents in the molten material as it cools, and those currents create imperfections that scatter light and reduce the fiber's performance. In microgravity, no convection, no currents, and the resulting fiber is dramatically better. We're talking about fiber that could carry signals with significantly less loss over long distances. Companies have already manufactured small quantities of ZB-LAN fiber on the ISS, and the results are promising enough that this could become one of the first real space-manufactured products with a terrestrial market. Or consider protein crystal growth. When you grow crystals of a protein in microgravity, they tend to form more slowly and more uniformly, producing larger, more perfect crystals. And the quality of a protein crystal matters enormously for pharmaceutical research, because better crystals give you better data when you shoot X-rays through them to map the protein's three-dimensional structure. That structure is what tells drug designers where a molecule can bind, how a disease mechanism works, what kind of drug might interrupt it. Crystals grown on the ISS have contributed to research on everything from cancer to muscular dystrophy. It's not that you can't do this work on Earth, you can, but microgravity gives you a cleaner, more precise result. There's also bioprinting, using three-dimensional printing techniques to build tissue structures from living cells. On Earth, gravity causes freshly printed tissue to sag and deform before it can solidify. In microgravity, the printed structure holds its shape, which means you can potentially print more complex tissues, maybe eventually organs. This is very early-stage work, but the potential is enormous. Imagine a future where a patient needing a new kidney doesn't wait years on a transplant list, but instead has one printed from their own cells in an orbital facility. That's decades away, if it happens at all. But the foundational research is happening now, on the ISS and on commercial platforms. So the economic case for space stations is slowly, tentatively emerging. It's not proven yet. Nobody's getting rich manufacturing things in orbit. The costs are still too high, the volume's too small. But the trajectory is clear, and if launch costs continue to fall, there's a plausible path toward a real space economy. And once you have an economy, you have a reason for people to be there that doesn't depend on government budgets or political will. You have something self-sustaining. And that word, self-sustaining, brings us full circle, doesn't it? Because that's been the dream from the very beginning. Tsiolkovsky's greenhouse cylinders, Nordung's three-part station with its solar collectors, von Braun's spinning wheel, O'Neill's massive rotating habitats at the Lagrange points. The dream was never just to visit space. It was to live there, to build places where human communities could thrive independently, where children could be born and grow up and never set foot on Earth and still have full, rich lives. We're nowhere close to that yet. Let's be honest about that. The ISS, for all its magnificence, is a place where 6 or 7 people live in conditions that are somewhere between a submarine and a very cramped apartment, utterly dependent on regular resupply from Earth. The water recycling isn't good enough. The food all comes from the ground. The radiation shielding is minimal. Nobody's having children up there. We don't even fully understand what microgravity does to mammalian reproduction, though animal studies suggest it's complicated. The psychological challenges of long-duration spaceflight are real and not fully solved. We know that isolation, confinement, and distance from Earth take a toll, even on highly trained, highly motivated astronauts. But here's what I keep coming back to. Every single one of those problems is an engineering problem, not an impossible one, not a violation of physics, just a hard problem that requires clever solutions, sustained effort, and enough institutional will to keep working at it. Radiation shielding? We know how to do it. Hydrogen-rich materials, water walls, possibly active magnetic shielding. It's heavy and expensive, but it's not mysterious. Artificial gravity? We've understood the physics since Newton. Spin a habitat, and centripetal acceleration gives you something that feels like gravity. The engineering challenges are real. Bearing systems, rotational dynamics, the Coriolis effects on human vestibular systems, but they're solvable. Closed-loop life support? We're at 90% water recovery now. Getting to 98% is hard, but achievable. Integrating plant growth is a matter of scale and optimization, not fundamental breakthroughs. The point is, none of this requires new physics. It requires better engineering. And if there's one thing the history of space stations shows us, it's that humans are remarkably good at better engineering when they commit to it. Every station was more capable than the one before. Every crisis produced lessons that made the next mission safer. The progress has been slow and expensive and sometimes heartbreaking, but it has been relentless. So as you're lying there, maybe drifting a little, maybe still following along, maybe somewhere in between, here's what I'd leave you with. Right now, tonight, there are people living in space. There have been people living in space continuously since November 2nd, 2000. Over 2 decades, without a single day when our species was confined entirely to this one planet. That's a quiet, extraordinary fact. Most people don't think about it. But somewhere above you, moving at 17,500 miles per hour, there's a structure the size of a football field, with humans inside it, looking down at the same Earth you're lying on right now. They're running experiments, fixing equipment, eating rehydrated food, maybe looking out the cupola window at a sunrise that comes every 90 minutes. And that station is just the latest in a line that stretches back to Salyut 1 in 1971, and before that to the dreamers who imagined it, Tsiolkovsky with his notebooks, Oberth with his mathematics, Nordung with his careful diagrams, von Braun with his magazine illustrations and television appearances, Korolev with his iron will and his ruined health, all of them reaching toward the same idea, that the sky is not a ceiling, that this planet, as beautiful and irreplaceable as it is, does not have to be the only place we call home. Whether that dream fully comes true, whether there are ever cities in orbit, or colonies on Mars, or habitats drifting in the space between stars, that's a story that hasn't been written yet. It depends on choices that haven't been made, by people who might not even be born yet. But the foundation is there. It was laid by hand, bolt by bolt, module by module, by people who spent their lives solving problems that had never been solved before. And every time you see a bright point of light moving steadily across the night sky, not blinking like a plane, just gliding, smooth and silent, that might be the station. That might be the place where, right now, someone is tending an experiment, or tightening a bolt, or just floating by a window, watching the world turn below. It's a good thought to fall asleep to, I think. That we built that it's up there, that the story goes on. Good night.